All right, I believe we are live. Thank you everyone for attending today's X-Space. My name is James Henderson. I'm a researcher here at the Newell Foundation working on zkSharding. Just a quick personal note about myself. I'm a keen rock climber and currently enjoying the second time it's been involved in the Olympics. The competition is currently on at the moment. So today I'm going to let you know about some work of ours that's a component of our system, and we call it the ShardDAG, as I've put in the title here. And the need for this is motivated by MEV and censorship, which are both current topics of interest in crypto and blockchains, and I hope of interest to you all today. If you have any friends that are not attending, but you also think they might find this interesting, please invite them here. All right, and we'll move on. Just give me 1 second. Okay, slides are working. Great. Okay, so before we actually get into it, I realize we may have a mixture of technical and non-technical people in the audience. So the plan is to first introduce the ideas in the broader context and then progress towards the technical details later in the talk. So I hope even for the later technical parts that the explanations are clear enough that anyone can understand. If you do have any questions, feel free to drop them into the chat. And also there'll be time at the end to ask questions and clarify if you need to. All right, so before we go straight into the ShardDAG, I'd first like to give a bit of a mini review of zkSharding so that we have some context for the type of system in which the ShardDAG would be useful. And also because perhaps some of you haven't come across zkSharding yet. So zkSharding is Newell's Ethereum Layer 2, which is being built to realize the original vision of a smart contract-based blockchain. So that is a substrate that supports the evolution of a vibrant, diverse ecosystem of composable applications. So it's a unified protocol in which dApps are composable. State fragmentation is avoided. As I'm sure you're probably aware, there's a whole plethora of different L2s emerging in the Ethereum L2 space, and that is itself some form of state fragmentation. And of course, so that Ethereum scales. And in this case, we're going to scale using state sharding. The typical picture of which is something like I've shown in the diagram here at the bottom. In case you aren't familiar, a state sharded system maybe diagrammatically looks a bit like this, where you have a set of distinct shards that each act a bit like their own blockchain. But the key point here is that each shard has its own set of smart contracts. So shard A here has its smart contracts, shard B has its smart contracts, and so on. And each shard is only able to interact directly with its own particular set of smart contracts. It can't interact directly with the smart contracts on a different shard. So let's say you want to make some reasonably complicated transaction that interacts with smart contracts that are distributed across a range of different shards, then you need to do something a little bit like what I've shown in this diagram, where you deploy your transaction initially in some shard. So let's say shard A here in this example, the blue one. It's picked up and included in a block. The transaction's processed. It does something with the smart contracts on shard A. And then as part of that processing, it outputs a cross-shard transaction whose destination is some other shard, in this case, shard B. That's this orange thing here. At some point, that's picked up by shard B, included in a block. Again, it gets processed, and as part of that processing, if it needs to continue on to interact with another shard, it produces another cross-shard transaction here in yellow. That gets picked up by another shard, here shard C, and you can imagine this process continuing on. But the key point here is really just that all these shards are continually processing and building blocks in parallel. So we have some parallel processing. And if we want to scale, we can scale horizontally by adding more shards. All right, so before getting into the technicals about the ShardDAG, I'd like to motivate it. As you've been probably aware, if you've been around blockchain for a while, but the last 10 or 15 years of blockchain, there's been a lot of focus on developing various consensus algorithms to ensure that on-chain data is secure. And the foundations of that are fairly well developed, and that's all great. But in more recent years, there's been a lot of emphasis placed on this problem, so parallel to that, in how do you actually get data on chain in the first place? Because that's potentially a dangerous and problematic thing to do. And in conjunction with that, the idea of MEV, or minor extractable value, has arisen. There's been lots of work on that. It can be seen, for example, as a centralizing force, and so there's been systems built like PBS as potential ways to counteract that. I'm sure you've probably all heard about transaction exploits like sandwiching and front running, where people try to insert transactions either before or after other ones to exploit them and make some money. There's potentially problems with censorship and regulation, where, for example, in the US government has decided that certain dApps are not to be used, they're banned, and so in Ethereum at least, block builders will not include any transactions in blocks that interact with those dApps, so therefore users get censored. And then there's sort of more exotic things like oracle manipulation, where you might try to influence the ability of oracles to get their data on chain so that you can do some DeFi stuff and make money. The key point here really is just that in a developing ecosystems, agents will find niches to exploit and make money and a living, much like in a living ecosystem, where if you have some low entropy energy source that's available in some niche, then it's likely you'll get some kind of organism that will evolve to exploit that niche. And we only really need to look at traditional finance to observe this, and consider industries like high frequency trading, where they have absorbed huge amounts of resources, building sophisticated hardware, software, going around hiring all the smartest people they can find just to eke out loads of small little gains on the individual transactions that together sum into some huge amount of money. And of course, blockchain is still new. If the blockchain dream is realized, where some large fraction of the global economy is conducted on chain, then more and more exploits will be found. So returning to this idea of the ecosystem, in a biological setting, the rules of the universe, or what you might call the laws of physics, dictate how ecosystems can develop. But in our case, it's, at least in a large part, the protocol rules that can govern the ecosystems that emerge. And what we want is rules that lead to the development of something of great value, like a beautiful rainforest. We certainly don't want something that's going to lead to some nasty sort of bacterial sludge equivalent in the blockchain ecosystem. And so that is the purpose of this ShardDAG, is to set up the rules so that we have a vibrant ecosystem. Now, all the above problems that I just mentioned exist in non-sharded blockchains, but it's a simpler problem than in a sharded blockchain. Because if you're operating in a non-sharded blockchain and you want your transaction to be processed, all you really need to do is to find one cooperative block builder that includes your transaction in its block, gets processed, and it's done. It may be the case that you have some transaction inserted perhaps before and after in order to exploit yours, but it's a simpler problem than in the sharded blockchain. Because returning to this idea of state sharding, as I showed you earlier, if you want to have your transaction processed, it potentially needs to get included in blocks that are distributed across many shards. And each time your transaction or its cross-shard transaction needs to get included in a block, there's potential there for exploitation and also censorship. And perhaps even more concerningly, unlike in a sharded blockchain where everything is processed atomically, it's all done at once. In a sharded system, it's possible for your transaction to be exploited partway through its processing. So that in one of these intermediate blocks, people insert some exploit partway through your transaction being processed. And obviously that can lead to more creative ways to exploit transactions. So the purpose here of the ShardDAG is really to constrain this censoring and exploitative behavior to ensure that a couple of things, that once a transaction begins on a shard, it will complete on another shard. It won't be blocked or exploited by a censoring shard or validator in a particular shard. All right, so to make this idea clear, I've got a simple example here on the right-hand side. So let's say we have two shards, A and B, and we have two cross-shard transactions that happen to be in shard A. The red one here is an exploitative cross-shard transaction in that if it's processed earlier than the blue one, then that means that it can exploit the blue cross-shard transaction. So in a naive system, a naive sharded system in which you don't have any rules around the order in which cross-shard transactions must be processed, then you could have a situation where the blue cross-shard transaction at the bottom could be included in any one of the blocks on the right-hand side in shard B, and perhaps the red one could be included in the top two blocks, block 1 or block 2. And if it just happens that for whatever reason that the blue cross-shard transaction, let's say, gets included in block 2 at the top and the red one in block 1 in the middle, then that means the red one is processed earlier than the blue one, and therefore it can exploit the blue transaction. Now, obviously, the way that you can sort of get around these exploitations, or prevent them, I should say, is by having some rules around the order in which transactions must be processed. Namely, that earlier ones have to be processed before later ones. But this isn't actually such a simple problem, because if you want to enforce rules around the order of which transaction should be processed first, then if you think about it, if shard B is the one that actually has to do the processing and you want it to obey certain rules, then it needs to be penalized if it breaks those rules. But let's say, for example, that shard A is somehow malicious, or perhaps just Byzantine in some general way. Maybe it's not able to share its data as it wishes. So let's say that it just withholds this blue transaction for a period of time, so that shard B is just not even aware that it exists. But for some reason, it's able to distribute, or deliberately distributes, this red one earlier. So shard B might pick that up, put it in a block, and then only later it gets sent the blue one. So it wouldn't make sense then to penalize shard B, because it just didn't have data delivered to it in the right order, and it wasn't aware that there would even be this later blue one that gets exploited by the red one. So in order to make these rules around the order in which things can be processed, we really need a mechanism for establishing cross-shard transaction data availability, and everything really rests upon that. All right, so the strategy that we employ in the ShardDAG is that we want a combination of protocol rules, rewards, and penalties to constrain the ability of validators to manipulate the processing of their transactions. So that's our goal here on the right-hand side here. We want our transactions to complete and constrain the ability of people to just fairly arbitrarily exploit things. As I just described, in order to put some constraints on those things, we need to enforce the order in which transactions and cross-shard transactions must be processed. But in order to have an order of processing, we first need shards to receive those cross-shard transactions that they need to process. But then, of course, in order to be able to receive those cross-shard transactions, we have to have that data available in the first place. So again, everything rests upon this idea of enforcing data availability of cross-shard transactions. All right, so this slide here is just going to be a first introduction to the ShardDAG. It may look a little bit complicated, and perhaps you may not get everything on this first go, but I'm going to return to this slide at the end. So if you don't get it the first time, don't worry. As we go through, hopefully the ideas will become clearer, and we'll go through it later as well. All right, so as the name suggests, in the ShardDAG, we're going to make use of what's called a directed acyclic graph. So that's a sort of a mathematical construct or a mathematical object that's used to describe ordered systems, in particular partially ordered systems. So instead of having a sharded system like I showed you earlier, where we have different blockchains, for example, this shard B connects to its previous block, and that this block here connects to its previous block, just like your typical blockchain. We're going to link together shard blocks from different shards together. So for example, the top block here connects to this cyan colored one through some kind of link in here, and that's what gives us the DAG as opposed to sort of a linear blockchain. And the reason that we do that is because that allows us to identify ordering between blocks that are produced in different shards. So for example, this yellow shard block, we can see that it occurs before the green one. And let's say this bottom greenish one here occurs before the cyan colored block. And so once we're given a DAG, perhaps maybe some of you are aware that if you have a DAG, you can visualize the order of things within that DAG through what's called a hash diagram, which I've shown here in the middle. It's not exactly a hash diagram, but the idea here is just to give some visualization. And we can see, for example, that we have what's called, again, a partial order, which means that there isn't necessarily a relative ordering between all the different blocks in the DAG. So for example, all these red, green, and blue blocks that are at the bottom, according to the DAG, there's no way of actually distinguishing sort of which one happened before the other. So they all have sort of an equal ordering. But we can say, for example, that they all occurred before the, say, this orange one here, which occurred slightly later. And right at the top, we have this block here that we're focusing on at the moment. So if we imagine that we're a validator in shard B, or perhaps just some node in general that just sort of wants to check that shard B, this block 2, has been produced correctly, what we do is we do what's called a topological sort of the DAG, which means that we just order all of these blocks directly one after the other. So not a partial order, but a total order. And then in terms of working out within this block that we're focused on at the top here, perhaps the block that we're trying to build, if we're the proposer or the builder, we have an ordering of transactions, which I've shown in these colors on the right-hand side, that inherits the same ordering of the topological sort of blocks in the shard DAG. So returning to the visualization in the middle, we can see, for example, that the red, blue, and green ones all get processed first, where I put the transactions that get processed first at the bottom. But again, there are many ways you can do this topological sort because we have this partial order. So we can have, say, the red one happen first, the blue one be processed first, or this green one be processed first. But again, they can be permuted amongst each other, but they have to happen before, say, this yellowish orange one. All right, so that gives us the rules around ordering. And as you can see from the previous example of the exploit, it ensures that, in general, things that happen earlier are processed before things that happen later. All right, so the immediate question then is, how do we actually build this DAG structure into the blockchain? It's relatively simple. We just need to modify the shard block header. So in a typical block header, you'll have a hash to a previous block. So if we consider this white block here in the diagram, it has a hash to the most recent block in its own chain. So we keep that. But we just extend the block header to also include a set of hashes to some other shard blocks that I've shown here. This white block is linked to the middle shard B block. And we also have a hash to a synchronization chain block. I'll describe what the synchronization chain is about in the next slide. But the thing that I really want to focus on right now is that what's written in red here. So if you suppose that you're a block builder, or the validator proposing this white block here, when you create that block and you choose those particular hashes, what you are doing by choosing that hash is to acknowledge that you've received all the cross-shard transaction data that exists within that block. So if we include this shard B block here, shard A is acknowledging that it's received all the cross-shard transactions in that block. But not only that block, but every block that falls under it in the DAG. So everything down here that can be traversed through the DAG to connect to this block that you've got a hash to. And the same applies to the synchronization chain. If you choose to include this synchronization block here on the left, that means you have all the cross-shard transaction data of everything that is under it. Okay, so we're going to start getting into this strategy that I described earlier, starting on the left about data availability. But just before I do that, I'm just going to say a couple of words about the synchronization chain, because that may not be something that's clear to people. So I won't say everything about it, but I'll just kind of focus on the points that are relevant to the ShardDAG. And the key point really is that in our system, the way it works is that the synchronization chain, each block includes blocks from the various shard chains. And because zkSharding is going to be Ethereum layer 2, there's some sort of sync committee that aggregates the state updates from these different shards and then puts them on the L1. And so really the key point here is that if you're a block builder in one of these shards and you want your block to get finalized, it has to get included in the synchronization chain. And of course, you want your block to get finalized because you want to get paid for your validated duties for signing or proposing these blocks. So we're going to use that economic incentive to get included in the synchronization chain. All right, so now we're really going to step into the more technical details. And first, we're going to look at how we do this first step of enforcing data availability of cross-shard transactions. And the way we do that is to create a block finalization condition. And the condition is really that if you have a block, so in the description in the diagram on the right-hand side, this white block here, if that block wants to be finalized within the subgraph of a consensus chain block, so in the top left here, if we look through everything that falls under it in the DAG, we cut out that piece of the DAG, we have what's called a child condition. So this white block, if you trace upwards through the DAG, through all these white arrows that I've highlighted, you should be able to reach child blocks that are created by more than F shards, where F is a protocol parameter that controls the rate of branching or spreading in the DAG. So in this example here, we have this white block that can be finalized because if we search upwards through the DAG, we can reach another block in shard A, we can reach another block in shard B, and we can also reach another block in shard C. And if we have, in this example, F is 1, we have 3 shards, which is greater than 1, so it can be finalized. In comparison, this bottom right-hand side gray block is not finalized because if we search upwards through the DAG, we can only reach its own shard, so only 1 shard, which is not enough to meet this child condition. That doesn't mean this block will never be finalized. All it likely means is that we have to wait for the DAG to be extended by new blocks being produced, and at some later time it will meet this child condition and it can reach finality. But the key point really here is that when this white block is finalized, that means that all these shards, which it can be reached, have acknowledged through including these hashes that they've received its cross-shard data that's in this block. And so here we're establishing the data availability of cross-shard transactions. All right, so the second step in our strategy is to enforce, now that we've got data availability of cross-shard transaction, is to enforce that shards actually receive these cross-shard transactions from each other. And to do that, we have what's called the parent condition, which is a condition on a shard block being valid. So a valid shard block must acknowledge receipt of new shard blocks from more than F other shards. And by that I mean, by new, I mean compared to its most recent block. So again, looking at the example on the right-hand side, we have this white block that is a valid block, because if we search downward through the DAG, we can see that, well, this new block itself counts as a new block that was not in its previous block subgraph. So it's one shard. We search down through the DAG through these thicker gray lines. This happens to go through the synchronization chain, and we can see that there's a new block in its subgraph from shard A, which was not in the subgraph of its previous block here. So it's got 1, 2 blocks that were not in the subgraph of its previous block, which is more than 1, so therefore it's valid. In comparison, I've put sort of an example of an invalid block in shard C at the top right here with these dash lines. And that's invalid because if we trace downwards through the DAG, we see that it reaches its previous block, which was in its previous block subgraph, so that's nothing new. And we trace down and we can see the first shard B block here. That was also in the subgraph of its previous block. So this block hasn't included any new blocks, which means it hasn't acknowledged receiving any new cross-shard transactions, which makes it invalid. So the condition is really about enforcing validators to acknowledge receiving new cross-shard transactions from other shards. And of course, if you're a validator and you want to get paid, you want to produce a valid block, so you make sure your blocks link to these other new blocks, and you have to receive that information, the cross-shard transaction information. All right, so even though we had that previous parent condition to enforce receipt of cross-shard transactions, it could happen, even though I think it's very unlikely, that we have a situation, as I've depicted here on the right-hand side, where we have groups of shards, so here 1 and 2, that acknowledge receiving each other's cross-shard transaction with these hashes. So they form hashes to each other, but then you might have some other group of shards, say 3 and 4 over here, that also produce valid blocks that have hashes to other shards. But there's no hash or no DAG edge that goes between these two sets of shards, as I've shown in this dotted line in the middle. And so you can potentially have a situation here where, let's say you have a cross-shard transaction in red here at the bottom left that needs to reach shard 4 in order to be processed. But without having any DAG edges between these two sets of shards, the cross-shard transaction at the bottom never has to get acknowledged by shard 4, where it needs to be processed, and therefore it never enters this ShardDAG ordering system, and it doesn't get processed. So I think it's unlikely to happen, but we want to have a rule that forces shards to eventually always acknowledge cross-shard transactions. And so if you imagine that, let's say shard 4 was really malicious, and for some reason it just didn't want to process this red cross-shard transaction, what it would have to do would be to set up a situation like we've got shown here, where it only links to some other shard blocks that don't include that. But also it would have to choose hashes to synchronization blocks that don't have this red block here in its subgraph. So like in these solid blue arrows here. And so the way that we force it to actually include this red cross-shard transaction in its subgraph is by placing a condition on the number of consecutive blocks it can produce that link to the same synchronization block. So here, if we limit it to a maximum of 2, at this third block at the top here, we've got this dashed blue hash, which would no longer be valid. And so it has to form a red link here to this new synchronization block, which does have this cross-shard transaction in the subgraph, which means that this enters the subgraph of the destination shard, which means it enters the ShardDAG ordering, and at some point it will be forced to be processed. That is gives us a guarantee that eventually all transactions will be processed, because they'll be forced to include them in their subgraph. Every shard will be forced to include them in the subgraph. All right, so now that we've established this data availability. We've enforced the receipt of these cross-shard transactions. The next step is to enforce some particular ordering of cross-shard transactions, which I spoke about towards the start of the talk. So just to kind of review quickly, what we do is we do what's called a topological sort or ordering of the ShardDAG. And so we form a linear order of transactions and cross-shard transactions within a block. And as I alluded to a little bit earlier, this is a combinatorial optimization problem. So there's many possible topological sorts that we could produce from any given DAG. There are actually fairly simple topological sort algorithms, for example, Kahn's algorithm. It's not actually as complicated as it perhaps might seem. But where the complexity really does come in is that if a validator that produces a block wants to get paid as much as it can, so MEV, then it becomes a complex problem of trying to decide which particular topological sort to choose. And I think ultimately when the system matures, that's what will drive the decision about which one to choose. But at least there are simple algorithms for performing the topological sort. And also for confirming whether a given topological sort is consistent with the ShardDAG, so you can check the validity of the ordering. All right, so this is the diagram that I showed towards the start of the talk, so we can review that again. So really the point of this diagram is to show the protocol rules about if you're trying to produce a new block. So let's say you're a validator in ShardB and you're trying to produce ShardB block 2 at the top here, or you're trying to verify that it's done correctly. Perhaps you're another node or another validator trying to sign this block. The process is that you extract from this block's subgraph all the unprocessed transactions, cross-shard transactions, which are highlighted in colors here, and then you topologically sort them, which means that you put them in a linear order that is consistent with the order they inherit from the blocks that they're created within. And there are many possible topological sorts because we only have a partial order, meaning that some of these blocks can't be distinguished which one comes before the other. But there is still some kind of guaranteed ordering here that certain blocks, for example, these ones at the bottom, we know they have to happen, be ordered earlier than later blocks that fall after them in the DAG as you trace through the edges in the graph. Couple of points to note. Let's say that there is something that exists outside this subgraph. So let's say shard A has actually produced a block at the top on the left, and it has some cross-shard transaction that has a destination in shard B. Well, shard B can't actually include that in its block because there's no way to define the ordering relative to everything else. So if shard B did want to process those cross-shard transactions in a block that isn't in its DAG, well, it would have to create its block with a hash to that other block that's not included in the diagram. And then it would fall into the DAG and it could be ordered relative to everything else. So processing anything outside the block subgraph is invalid. Of course, it could happen that one of these shard blocks that has cross-shard transactions actually has more than one. So let's say this red one at the bottom here has 2 or more cross-shard transactions in it that have a destination in shard B. When they're included in the block in shard B, they have to be included in the same order that they're created in within say this red, shard A block 0. You can't go and fiddle around with the ordering to reorder things. Okay. Now, those of you that have been paying attention might immediately realize that there's a potential problem here, that we can perform this topological sort and sort our cross-shard transactions into some particular order here. But what happens if there's too many of them? And we call this situation an overloaded shard. So if you're trying to build your block here, you have some constraints on the size of the block, the amount of gas that can be processed by the included transactions, or perhaps some data limited in bytes and the size of your block, whatever the case may be. So it could be that your block just can't fit all of these topologically sorted cross-shard transactions. So we have two options here. One is just to take the first transactions that are in the sort. So starting from the earliest transactions, you take, say, the red one, the blue one, the green one, and the yellow one, put those in your block, and that's it. And all the ones that are left over that don't get included, they get included in a block that occurs after the one that you've created. The ordering will still be retained. It'll just be moved to the next block, or a block that occurs after. The other option is we can allow priorities fees to dictate which transactions get included. So if we want to have that kind of situation, it might be useful for example, for a DEX, users might want to be able to pay some fees to have their transactions or cross-shard transactions processed before other ones. So if you wanted to do something like that, you can just sort of imagine we have this ordering in the middle. We just eliminate from the DAG certain cross-shard transactions based on their priority fees. And of the remaining transactions that are not eliminated, we can again do the topological sort and choose a sorted set that fit inside the block. They still have to have this topological ordering that's inherited from the DAG. And any of the remaining cross-shard transactions that are new, the transactions that are new that would have been included in this block that you're building, you can put them in what we call an outbox. So these transactions are not actually processed in the block. They're just included as data so that they can enter the ordering system to be processed in some later block, because we don't necessarily want to block users from submitting transactions at all. Of course, the problem with allowing these priority fees is that you reduce the constraints on exploitation, because it then does become possible to play around with the order of transactions. All right, so that's it. Before I open the floor to questions, I just point you towards this link here that will take you to some further details on the ShardDAG that have been posted on ETH Research. Again, if you're not already, follow us on X at Nil Foundation. You can check out our Discord or our website here. But at this point, I'll open the floor to questions. So if you have any questions, feel free to drop them in the chat. Okay, so maybe I'll start with a question that I had asked ahead of time. So I had a question that, is there any restriction in which shard blocks can be hashed together in the DAG? So maybe I'll move back a couple of slides. So if we're building our DAG like this, in this example here, where we're deciding which hashes that we actually choose when we're creating our block, at this point in time, we don't have any restriction on which shards can hash to each other. But if it does become a scalability problem where, sort of for networking purposes, to constrain bandwidth and so on, or optimize the usage of bandwidth, that we want to constrain which shards can connect to each other, we can do that. So, for example, you could maybe have some kind of hypercube arrangement where you have a defined set of neighboring shards, and you can only hash to those ones. But it needs to be done in such a way that all shards can eventually reach all other shards. Okay, I have another question, which is that it seems like validators need to store lots of messages. Does this eventually become a problem? This isn't something that I discussed in the slides because it's sort of an extension. But yes, it would be the case that this becomes a scalability problem because eventually every shard sort of has to receive the messages of every other shard, the cross-shard transactions of every other shard. But the way that we can get around this is through a sampling process. So periodically, each validator samples some finalized transactions of every other shard. And then, so the point really is that each validator only needs to store the cross-shard transactions from unprocessed cross-shard transactions. So once you have transactions that's completed, you no longer need to store its cross-shard transactions. So periodically, you can sample which transactions are completed and identify ones that you no longer need. Again, I haven't put the details of that because it's sort of a little bit more complicated and beyond the scope of sort of getting the general idea, but we can solve that problem. Okay, well, unless anyone has any last minute questions, I guess we'll wrap it up there. Thanks everyone for coming. I'll just quickly put those links back up in case anyone is interested in reading more. Again, you can find more on ETH research. Okay, thank you.